And yeah, if we can get gradient descent, and then problem is solved, right? And that's how, and then how we can get this, then the back propagation is really powerful technique to achieve it. The chain rule. Chain rule is the rule for differentiating a composite function that probably you studied in high school or somewhere. And when we studied this, yeah, what is it for? We may wonder. But it's super useful, very, very useful for calculating the gradient for those neural networks. So here, L is objective function or loss function. And we want to calculate a partial derivative for all elements in this weight matrix W. Weight matrix W2 is all the weights connecting hidden layer and output layer. So Kj means kth unit and jth hidden unit. The weights is assigned to each connection, right? And as you can see, this entire function is a composite function. So we can use chain rule. And long story short, it will be represented as the multiplication of this delta k multiplied by hj. And hj is actually the value, current value of this hidden unit. And this delta k we will see in the next slide, but this is actually the difference between ground truth and the current prediction. So this is Eller for kth output unit. It's very simple. It's just multiplication, right? Very, very simply we can calculate. And what about weight matrix connecting input and hidden layer? And long story short, it will be expressed again, multiplication of this delta j and xi. And xi is ith element in input data, and the delta j is something we can just consider it's a kind of Eller value in the jth hidden unit. So x or h is something we already have if we have input data. We just run the forward process. So what's missing is those delta. But those delta, you can just do math calculation, and we can derive based on the cross entropy loss, for example. You can just calculate. And it will be just difference between prediction and ground truth. Very simple, right? And also delta J looks a little bit more complicated, but it can be represented as what we already have. The only missing piece is delta K. Delta K. But delta K can be calculated by this equation. So we can just give inputs to the current model and calculate all the values, all the outputs of the hidden units and output units, and then evaluate the Eller, comparing ground truth and the prediction. I'm talking about training sample, okay? This is the training stage. And once we can get delta K, we already understand. Oh, we can get everything. We can get all the delta J of hidden units by Eller back propagation. It's a kind of automatic differentiation. Okay, then we can evaluate the gradient of this Eller function or objective function, or let's say loss function with respect to all the weights. So problem is solved. Finally, we set up the goal, we set up the model, we define how to move, and now we know we can do this, right? You may wonder, okay, what happens if it becomes very deep, but you can just check out by yourself. Everything is the same. Basically, the core idea will be all more or less the same thing, so let us skip it. Basically, everything can be calculated by backpropagation. Okay, due to time limit, let me skip some parts. So normalization, maybe you are familiar with normalizing input data to make the value range consistent among different samples, but there is a technique, batch normalization. So batch normalization is inserted into after each layer. And it was found as very, very powerful technique in terms of optimization, or when we want to make the model deeper. And yeah, people point out that it's making optimization geometrically smoother. But due to time limit, let us skip that. The batch normalization is performed for each mini batch, okay? And as you can imagine, there are so many options how to normalize it. In case of transformer, maybe batch normalization doesn't make sense because normalization shouldn't be done with respect to batch, but maybe it's better to do this for each token, like layer normalization. So there are many options, but due to time limit, let us skip it. But when we implement it, we can choose what kind of normalization, and it depends on the task, what kind of task we want to tackle. And dropout is when we design a large model, maybe we can just disable many units and just use kind of virtual subset, sub-model, depending on the different samples, so that we can get kind of an ensembling phenomenon of smaller models. But this is also the technique commonly used for various models to make the model more robust. But let us move forward since we have still many pages. Data augmentation. If we have limited amount of data, in case of image processing, maybe we can apply some image degradation, blurring, adding noise, or changing color, or rotating, flipping, this kind of thing, so that we can increase. If we have 1,000 samples, this augmented data, maybe we can increase it to 10,000, for example. And the last part before entering hands-on, maybe example is, yeah, we will deal with image. Actually, I'm handling image data. And that example, what we have seen, this kind of fully connected neural network may not be the best option for image, right? Image is very huge. So many pixels. So the number of weight parameters become incredibly large. So we want to avoid it. And in image processing, yeah, very classic image processing, we usually rely on spatial filtering. Spatial filtering, so image, as you may know, if you zoom into the image is composed of different, so rasterized pixels. And each pixel has the value for blue, green, and red channels, 3 channels. But if we pick up red, each pixel may have 40 or 30 and so on. It's just tensor data, just number, okay? So spatial filtering is we prepare some spatial kernel or filter as shown here. And spatial filtering is to apply multiplication and addition. So in this case, apply -1 to 40, -1 to 40, -1 to 30, and so on. And then take addition. So it's a kind, again, it's a inner dot product. It's just calculating correlation. You can consider in this way. So it's something, we have spatial kernel, and the kernel is checking similar patterns. If there is any similar pattern, it returns high value. If it's low, if there's no correlation, if returns 0. If it has negative correlation, it returns a minus. In case of normalized version, but you can consider it's a correlation operator to check out the similarity between spatial kernel and the local patch. And this spatial filtering can be applied in a spatially invariant way. So very small kernel can be applied to entire imagery. So if we apply so-called solver filter, this kind of imagery becomes like this. Actually, we apply first order derivative in horizontal and vertical direction and calculate magnitude of such gradient imagery. And then it becomes like this. So it shows the edges, okay? When we recognize something, oh, there is a PC or whatever, whenever we recognize, this is because probably we are recognizing some edges, right, or some corners or some patterns. If we cannot identify any edge, then maybe we cannot identify anything, right? So this is very, very basic spatial filtering, but, and then, yeah, derivative filter is actually images, how to say, delta x cannot be smaller than 1. So in case of image, it's just difference between neighboring pixel, right? It's very simple. But spatial filter kernel can be designed if it's 3 by 3, horizontal direction or vertical direction. It can be designed in this way. Okay. The example that I have shown is the magnitude of this derivative filter using solver filter kernel. So convolutional neural network. This is a very famous one in the last 15 years, let's say. So basically, the entire process is similar to what we have already seen for fully connected neural network. But the weights are spatial kernels, okay? So what we want to optimize is spatial filter kernel. If it's 5 by 5, the training is corresponding to optimizing what kind of pattern we should look at. So these spatial filter kernels weights will be optimized. So that is corresponding to matrix W1 or 2 in the previous example. So if we want to extract the different features, we can prepare different kernels, right? Oh, this kernel is responsible for detecting vertical edge. This kernel is responsible for detecting corner. We can prepare many, many diverse kernels through training so that the model can identify the local patterns. And then such patterns will be merged as a little bit higher abstract information through pooling layer, because image recognition, if image is slightly shifted or moved a little bit, if the output is totally different, it's not good, right? And also, if we extract more and more features, if we keep original resolution, it's a little bit, how to say, the dimension of the volume of the spatial feature maps will be too large. So pooling layer is to merge, spatially merge those features and apply spatial filter kernel, pooling, spatial filter kernel. So this is the typical way of convolutional neural network. So we have already seen spatial filter kernel. So if we just scan this kernel within the input image, usually feature map becomes a bit smaller. And stride is, whenever you implement something, you can set up kernel size or striding, stride as one thing that you can set up. You can skip 1 pixel by setting stride 2. If you want to keep the same spatial size as input, you can add some virtual pixels around the input image. So that's the scanned feature map has the same size. And this pooling is to, spatially get some maximum value or average value. Okay. So CNN showed very outstanding performance on the image classification benchmark. So benchmarking is very important and people just try to try many different things to figure out what is good, what is bad. And 2012, AlexNet won the game. And at that time, the model was like this. Oh, people were like, oh, this model could be trained. And then performed very well and having very large difference between first place team and second place team. And this table shows the structure details, so I hope now you can understand what is stride, what is padding, kernel size, input feature channels, output feature channels, number of parameters. So people are aware that if we can make it deeper, performance should be better. But it was difficult. But 2015, actually in this paper, and this team led by Professor Kai-Min Hu, they won the game. And they achieved very good performance, and they succeeded in making the model deeper. And the core idea that they proposed is residual network. So previously, convolutional filter kernel, batch normalization, nonlinear function, just repeat this again and again. When it becomes deeper, usually features shouldn't change so drastically, right? It should change slightly. But enforcing the network to learn identity mapping is just burden, right? So what they propose is very simple. Oh, network should be only responsible to how to slightly change. Let's just learn residuals. So the input is passed to be added as the output of this block. In this case, this part no more need to take care of constructing identity mapping, but instead it's just focused on how to change. So it's something similar to us, right? We have some goal, we want to improve ourselves, but what we can do is we are here, we are like this, so we can slightly change ourselves, right? We cannot drastically change ourselves, so let's focus on just residual change. And then they succeeded to make it deeper, and due to time limit, let me skip this one. And people say, oh, neural networks are black box, we don't know what's happening, but now you understand. It's not black box, come on. It's just a composite function, right? So you can just take a look inside. For example, this is a very nice gradient weighted class activation mapping. This is to check out which feature, where the model is looking at spatially by calculating the importance of different features, and try to visualize the activation by considering such weight with respect to the prediction. So for this prediction, the model is looking at this area. So we can see this kind of thing. Maybe I explained a bit slowly. So yeah, transformer. Transformer is everywhere now, also for image processing. CNN was powerful, but people use vision transformer. And originally it comes from natural language processing, but here is an example applied to image processing. So vision transformer, if you are interested in, you can take a look at the original paper. But they try to imitate the original transformer in NLP in order to see how it works for computer vision tasks. So entire image is split into smaller patches. So actually there is no spatial filtering, right? Just split entire patch. And each patch is regarded as each token. And each patch is converted to a fixed size of vector by linear transformation. And it goes to something. And let's take a look. What is it? This encoder is, again, lots of layers and blocks. And for each block, it looks like this. So now we can see, oh, there is a residual connection. Okay, so residual learning is kind of standard. So let's learn how to slightly change. And here, there is self-attention. So this self-attention is this ML, multi-layer perception. This is fully connected neural networks that we have already seen. So what we are not aware of is this self-attention. So the first step is just a linear transformation, and if we want to classify entire image, we need to also prepare some vector for taking care of representing entire imagery, which is called class token. But what's important is self-attention. So each patch will be each row vector, and if there is any class token, it will be like matrix. And self-attention is explained. Oh, self-attention is, we can obtain with this equation using query key value matrices. And this is for someone who just look at this equation for the first time. Maybe this is not really intuitive. So what's happening here is to take in two matrices having the same number of patches plus 1 in case of we have class token. It's just calculating, again, Q multiplied by a transposed K is, again, correlation. It's just calculating correlation to check out which one and which one has high correlation or low correlation. And use such correlation weights to create, actually to transform this X. So this weights is applied to this value matrix and transformed. And what sounds strange, what may sound strange to you is all query key value matrices are made by linear transformation of input matrix X, which sounds a bit strange, but this is not really mathematical way of explanation, but let's say it's a more intuitive way of explanation is that we want to improve ourselves, right? In order to achieve the goal, we want to slightly change the features of what I mean, each of us, maybe each of us is this each row vector, okay? There are so many excellent people here, and around us, there are so many good examples, maybe bad examples as well. But when we want to improve ourselves, we may look at someone, oh, this person has some similar aspect as mine, but in this aspect, he or she is very good on this task or something. So maybe we refer to someone who has some correlation with us. Or we may look at some people who has very low correlation. Oh, this person is totally different, and maybe that's why he or she is like this. But depending on the situation, depending on where we want to go, how we want to improve ourselves, we may look at correlation with other examples and then define how we should change ourselves. So maybe this is really an intuitive way of explanation, but this is what's happening here. So the matrix is just rotated. It's linear transformation. It's just, you can consider it's a rotation. Rotating data and try to see the correlation to figure out better way of how to change for different different tokens. To achieve the goal is depends on the task. Maybe it's classification, it's regression, or maybe this is something, it depends on the problem. Okay, that's I hope you get some intuitive understanding. Oh, when we want to improve ourselves, let's find good examples or bad example to define what to do, where to go. Yeah, due to time limit, let us skip. It's just splitting the data into different sets, and yeah, the core part is done. So the first, it's called hands-on, but I explained a bit slowly, so we may not have enough time. But let me just quickly show you what is it. So I hope this PDF is already shared. So you can, this is AIST is one big institution, research institution in Japan, and they made a building change. It's a classification data set using remote sensing image as input. And in this page, in PDF, the link is embedded, so you can just click, and it will show something like this. So the only thing you need is you need a Google account. So if you want to quickly run it, please, if you don't have it, yeah, maybe you can make it. And you can open it with Google Collaboratory. If you are familiar with it, yeah, no need to run it. If you are not familiar with it, please open it, Google Collaboratory. And I recommend you to, sorry, this is in Japanese. I recommend you to, there should be, it's written, copy and save into your drive, into your Google Drive. So, yeah, please copy and save this into your Google Drive. Maybe now you may not have time, so maybe you can do it later. So here is just an example. So on the internet, you can find lots of excellent materials, so no need to stick to this example, but this is something consistent with what we have seen so far, and this is using this nice data set as examples. So this is, so due to lots of like transformer or CNN, whatever, everything is matrix and vector calculation, multiplication, and that's why, yeah, GPU is needed. So please use GPU mode. I think you can set it up. There is a setting of notebook, and yeah, usually it's indicating GPU, but if you run it with CPU, and then it never ends, so please be careful. So it's just examples, importing libraries and getting data. And depending on where you want to save your data, please change this kind of path by yourself. Firstly, copy and save this on your Google Drive and change the path depending on where you want to save. You can do it later. And download data and zip it. And these are set up defining some data transform, normalization before putting the data into the model. And these defining data set or data loader, you can decide what kind of batch size, how to sort out the training data and pass it to the model. And this is just function to visualize data. And this data is for classification of destroyed or survived. So this is the aerial imagery, remote sensing images over damaged buildings after tsunami. So there are some washed away image or some buildings survived. So this 1 or 0 is corresponding to binary two classes, okay? Destroyed or survived. And yeah, here is training, and let me see. Oh, model setup here, yeah. By the way, this is based on PyTorch. PyTorch is so nice and it's so convenient. Lots of complicated things can be written with one line. But you can see here, this is very important. Loss function. You can change. You can even write yourself. You can decide what kind of loss function. But yeah, cross entropy loss or SDG, stochastic, SGD is a stochastic gradient descent. There are many, many nice optimizers, but here, just an example, learning rate and momentum. This is corresponding to the beta that we have seen. So without any knowledge, maybe it looks like just magic numbers, but now you all know, oh, this is step size. Oh, this is for the parameter of momentum. And here is very important. So loss function and optimizer, these are important. And here is defining the model, but this PyTorch is, lots of nice models are already available. So it's just calling VGG16 model, but yeah, ResNet can be also loaded if you want. And it's just visualizing the size of output and what kind of layer, convolutional layer, batch normalization, LeLu function. I hope you can see, oh, this is so simple. It looks complicated, but now you can understand. Each element is not that much complicated. And training. Yeah, here you may need to define the epochs. Just for convenience, I just set it to 10. And it takes some time. And after that, for inference, for training data, and for testing. For testing, we only have input images, right? Okay. And what's very important is we should separate training and testing. Okay, we shouldn't mix them up. So this is for testing data. Or I hope this is for testing data, but maybe I use it for validation data. I'm not sure. I need to check. So usually among training data, we use part of this as validation data, never used for updating the parameters, but try to decide when to save the model. Or so basically for training data, the loss will, if it goes smoothly, it's just decrease. But if the performance doesn't increase and just drop for the validation set, maybe we are making the model overfitted to the training data. So maybe in this case, we should stop the training, or maybe validation data can be used to figure out what kind of hyperparameters, like there are some hyperparameters that we can set up. not the model parameters. So such for model selection validation set is, can be used. But anyway, this is an example of prediction result for the samples that are not contained in the training data. Result is surviving, ground truth, GT is surviving. Okay, it's correct. And this is washed away, it's correct, and so on. This is just visualizing the inference for the samples not contained in the training data. And this is GradCam, I think, to visualize where the model is looking at. So the model decides that this is surviving by looking at around here. Surviving, washed away, surviving, washed away. So hopefully you can see for surviving, it's looking at some objects like buildings, right? And for washed away, it's looking somewhere, some entire region or some debris or. So I hope now you can explain to other people. If someone says, oh, this is black box, you can say, no, 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 it's not black box. You can visualize it. We can understand where model is looking at, okay? We shouldn't say it's black box. It's just composite function. So we can analyze in this way. Yeah, that's all for this example. Oh, there are so many. Okay. Okay, then let us go back. We have 7 minutes only. So not that much time left. But for semantic segmentation is to classification of every single pixel. So naive idea is crop each patch and classify them so that we can get classification result for every single pixel. But that is a little bit not that much efficient. So classic approach usually from original data extract features and perform classification for stacked feature vector for every single pixel. Now this is very straightforward. And what we should do for CNN or similar to transformer. So CNN, spatial dimension will be lower, right? More and more high-level feature, abstract feature, we extract spatial feature has low resolution. But we want to get the same resolution as input. In this case, we need to make the resolution back to the original spatial dimension. So we need a kind of decoder. And we pass these encoder features through skip connection, for example, the typical way to do this. And decoder can be responsible to how to make it back to the original resolution to perform classification for every single pixel. And evaluation metrics, yeah. For multi-class classification, intersection over union, for example, or if it's binary classification, we also use F1 score, this kind of thing. Intersection over union is quite simple. Number of samples of intersection between prediction and ground truth divided by combined region. So it's represented as the number of true positives divided by the number of summation of true positives, false negatives, and false positives. And due to time limit, let me skip the next one. But yeah, cross entropy, some people say, oh, it's putting penalty too much for a good prediction. So there are some other options like focal loss, or if the segmentation is the target, we can use such metric as the loss function. And the last is just an example of the data set I shared with you. as the second hands-on example. So we built up nice segmentation data set covering many countries or regions. So in this case, the input is image, output is labels for every single pixels, right? Okay, so the label is not for entire image. Labels are given for every single pixel. We can skip these parts. And yeah, here you can find example. If you want to run the training, yeah, maybe this sample code here is a good option to start. And some other examples trained on the full data set is also available. And this sample, since the data is not that small, I just extract a subset so that you can run it on the Google Colaboratory, just an example. But once we train a model for given this kind of imagery, now you will be able to get this kind of map. This image, this kind of map. This image is from Japan. This one will be like this, and so on. So if there is any disaster happen, what we need is input imagery. And we can find some changes without any tuning. This kind of off-the-shelf model works pretty well. And for Japan, for example, Japanese GIS authority, they released aerial imagery. So you can, if your country has such high-resolution aerial or satellite imagery, yeah, you can raise your hand and, okay, I can be responsible to take the map of my country. So you can now do this, actually, by running this kind of model. Okay. And some other example, not only classification, but also height estimation. We also made a height estimation data set. The problem will be not classification, but it will be regression. But the models are more or less the same. So what we need to change is we need to change the data. We need to slightly change the loss function and so on. But this kind of height estimation will be also possible. And by opening this kind of, yeah, since time is up, I just quickly show you. Here is another example that you can jump from this one. Again, please copy and save it into your Google Drive and just run it. So yeah, importing libraries, downloading data, and so on. Image size, batch size, number of epochs, and here is an example of images and defining, yeah, here is defining network. Oh, optimizer is set to slightly different ones, but yeah. And it takes time, actually. Now the task is more complicated. It's not really a small image. It's really processing a little bit large image and classify every single pixel. So it's a bit complex. So training takes a bit of time. But if you have your own GPU computation or some server that you can submit your job, I just stop it at epoch 30. And that's why prediction results are not really good, not as good as what I have shown here. The data set is subset and training is stopped at the middle. That's why it's not really good. But if you have enough computational resource, yeah, you can give a try to train with full data. And then you will get this kind of very, very nice good model that can predict in this manner. Yeah. I think time is up. So yeah, I think it's time for coffee break, right? So if you have any questions, I may stay around here. So that's all from my side, and I hope you enjoyed, and it could be some inspiration.